week. So last week you have learned about the ranking cycle. So this is the ranking cycle, and so you learned about two versions: ideal ranking cycle as well as the actual ranking cycle. So the actual one would look something like the one on the left, but the one that we will analyze will actually be the one on the right. So whereby we will assume all the pressure are still constant, then we get isentropic efficiency for both pump and turbine. So those are the ones that we assume they are not the same. So we discussed, we have examples on how to calculate the efficiency. So here we quickly okay, today we will study what are the factors that affect the efficiency of the ranking cycle. So in essence, how do we increase the efficiency? So here you can see, so steam power plants are responsible for the production of most electric power in the world. So steam power plant is actually very common. Just to mention this, steam power plant is not hydropower plant, okay? It's just a power plant that utilizes water as a substance, but it is not hydropower plant, because hydropower plant basically just water pushing the turbine. In this case, that's not the case. Okay, so now a small or slight increase in thermal efficiency will lead to large fuel savings. So which is also why we always strive for better efficiency. So two basic ideas on how we can improve the efficiency of the ranking cycle. The first one, increase the average temperature of heat input in the boiler. And the second is to decrease the average temperature of heat rejected in the condenser. Basically, what we are trying to say here is this. Let's come back to this. Let's look at the ideal ranking cycle. Basically, what we are trying to say there is this. Just now, so the two ideas there. Increase the average temperature where we are adding heat, or we reduce the temperature that we are rejecting heat at. So, meaning if you increase temperature at which you are adding heat, it means that you are shifting this up, right? Because you are heating it at a higher temperature. The other one then means that you are moving this down because you want to reject heat at a lower temperature. So what you are doing here is actually trying to increase the area under the graph. Do you still remember what represents the area under the graph? Volt net. Okay, so of course when you are changing, let's say the temperature input, of course Q in will also increase, but the overall idea here is that since thermal efficiency is Volt net over Q in, we try to increase this one. That's the general idea. Of course, again, if you increase the temperature, Q in will actually increase also. It's just that probably it won't be as much. So we want the area under the graph to increase. That's how we can increase the work out and also the thermal efficiency. So those are the two general ideas here. So increase average temperature, decrease the average temperature of, so one is for the input, one is for the heat rejection. So yeah, you can also see in this equation here. So we want to we want to either reduce this or we want to increase this. This is what we are looking at. Right, you want Q out to increase or Q in to reduce. Generally, that's the idea. Oh yeah, I got it wrong. Sorry about it. But anyway, we look at the three ways first. We will be clearer when we explain that. So the three ways that we can achieve this are this. So the first one is to lower the condenser pressure. So if you lower condenser pressure, then you are rejecting heat at a lower average temperature, because the whole line will get cooled down. Second, superheat the steam to a higher temperatures. This one very straightforward. Third, increasing the boiler pressure. So this one you are moving your entire line up. Okay, we look at that one by one, visually also. So first one, lowering the condenser pressure. So to increase the efficiency, the condensers of steam power plant usually operate well below the atmospheric pressure. So just now we said we want to reduce the average temperature that we are adding. We are rejecting heat. So which is why you can see in the diagram, from 4 we move the whole thing to 4 prime. 1 we move the whole thing to 1 prime because we are reducing the pressure. Okay, so that's what we mean lowering the condenser pressure. So you can see that from here, you are increasing the area under the graph, which means you are increasing the work net. But of course, don't forget, because of the shift in 2 prime, actually Q in also increase lah, because you are adding more things, I mean a bit more to heat up, because you are heating it up from a lower temperature. But this increase is enough to overcome that, so then your efficiency can be increased. So here, the limitation here for this method is there are 2. One, there is a lower limit to this pressure depending on the temperature of the cooling media. The limit will how should I say this? So the side effect from this limit is like what you see at the bottom. So there will be increased possibility of air leakage into the condenser, because if you are lowering the pressure inside the condenser, relatively speaking, outside pressure is higher. So it is more likely for air to go into the condenser itself. So then the other problem